Hi everybody, today I just wanted to start by just quickly revising what we did. So last time we did the central limit theorem and we found that the mean of the sample means is equal to the mean of the population, and the standard deviation of the sample means is equal to sigma, where sigma is the standard deviation of the population divided by root n, where n is the sample size. So I just want to quickly point out I had it wrong in the last video that these x's here were supposed to be capitals because they're representing the whole distribution of the sample means. So today we're going to have a look at a few examples of how we might apply this in situations. So we have a bottling company using a filling machine to fill plastic bottles with fruit juice. The bottles are supposed to contain 300 ml of juice, and we've got a mean of 302 milliliters and a standard deviation of 3.5 milliliters. So what's the probability that an individual bottle contains less than 300 milliliters? Well, in this case, where at the moment we're just talking about the standard distribution, so we haven't moved into the distribution of the sample means yet. So we represent this distribution by which is normally distributed with a mean of 302 and a standard deviation of 3.5, and so that's our distribution that we're working with, and so we want to know the probability of a particular bottle containing less than 300 milliliters, and so this is simply what we saw last week using the NCD function on your calculator. So we enter the lower value, which is 1e 1 times 10 to the negative 1 times 10 to the power of 99, the upper value, which is 300, the standard deviation is 3.5, and the mean is 302, and if we enter that into the calculator we get 0.284. so that means that around 28%, approximately 28% of the bottles contain less than 300 milliliters. So then it says, what is the probability that the mean contents of the bottles in a carry pack of 12 bottles is less than 300 milliliters? So this is where we're moving to now the sample distribution, or our distribution of sample means, because we want to know the mean content of a sample of 12 bottles. So we're working with the distribution where we have 12 bottles, or a sample size of 12, and we know that that is normally distributed, and so it has, from the central limit theorem, a mean of 302 and a standard deviation of 3.5 divided by the square root of 12, and to follow protocol we just square that. So that's the distribution that we're now working with, and we do not want to know that we want to know the probability that any particular sample of 12 bottles will have a mean less than 300. So that again we just use our NCD function. So it's negative 1e to the 99 is our lower value, our upper value is 300. Our mean is still 302, but now our standard deviation, in fact I should enter my standard deviation first. So our standard deviation is 3.5 divided by the square root of 12, and say, bear with me while I just fix up the formatting, so 3.5, so that's our standard deviation because we're using that distribution, and so but our mean is still 302 because by the central limit theorem the mean remains or is the same as the population mean, and so we get 0.0239 via our calculators. So that really means that around 2% of carry packets have a mean content less than 300 milliliters. So that's a good example to show where we use the standard or the distribution that we already had, but then for this particular example we move into a different distribution where we're looking at sample sizes of 12. Okay, so if we move on, our next example is looking at a tyre company have produced a brand new tyre and wish to advertise its mean legal tread life. They found from past experience that the standard deviation for the tread life of most tyre brands is approximately 3,000 kilometers. In order to estimate the mean legal tread life, a random sample of 60 tyres is tested. So what's the probability that the estimate gained is in error by less than 500 kilometers, sorry. So the error in the estimate is the difference between x bar, so the mean of our sample, and mu, which is the population mean. So basically it's just x bar take mu. Okay, so we want to know the probability that x bar take mu is between negative 500 and positive 500. And the reason for this is because the error could be, x bar could be less than mu by 500 or it could be greater than mu by 500. So we want to know, we've got to consider both directions of that x bar could go. So it's not entirely obvious where to go from here, but with the inequality that we have in the above line, if we divide everything by sigma divided by the square root of n, which is our, well, that's basically just our standard deviation for a sample size of n. So we go through and divide everything by that. So that's what we've done. All we've done is we've just gone through simply and divided everything by the square root of the standard deviation of a sample size of n. Well, really all this value here is just simply the Z statistic for our standard deviation, the Z statistic for our distribution of a sample size of n. So we can now work with the Z variable. So this is just a probability that Z, so we'll change this to Z because we know that we're working with that now, that Z is between minus 500 on 3000 on the square root of 60 either way, so minus 500 on 3000 on the square root of 60 and positive 500 on 3000 divided by the square root of 60. So in this way, using this rather neat trick, we've changed it to now be working in Z variables. So that's just simply the probability that the Z variable is between minus the square root of 60 divided by 6, and we're now working in Z, not X, and up to positive 60 on 6, and then we can just go and use the NCD function as we saw last week. So our lower value is minus the square root of 60 on 6. Our upper value is the square root of 60 on 6. Our mean, or our standard deviation, comes first, so that's 1, and our mean is 0. So if we put that into the computer, or rather into our calculators, which are mini computers, we see that that comes out to be 0.8033. And so that's what we've done. So we've converted to a Z statistic, because this formula here is simply how we convert from our distribution of a sample size of n to Z. Okay, so example 3 gives us two types of histograms, W and W bar. So this is the histogram of the sample means of W. And so they want to know which histogram belongs to which distribution. So often when we're answering these questions, we start by giving the significant part of the central limit theorem, and then make a comment about the distributions, and then draw a conclusion. So we can say that the central limit theorem states if random samples and I'll just pop an S there. If random samples are taken from a population distribution of any shape, then the distribution of sample means tends to become approximately normal. So now we make a comment about the actual distributions. So we note that A is approximately normal, while B is clearly not approximately normal. Hence, this implies that A is W bar, while B is W. So what we've done is in this section, We've stated what the central limit theorem says.